What's up, guys? Welcome back to Vanover Machine and Repair, and we have another interesting video for you today. We're going to be rebuilding this water pump. Let me bring you in close and give you a little bit more detail. Now, this is a fairly typical repeat job for us. We work with this pump shop. They do the rebuilding of the pump. They used to do their own machine work in-house, but have since outsourced that, and we're one of the shops that are lucky enough to be able to do some of this work. In this case, this job is a medium-sized job. Sometimes we do small little bushings for these pumps, and sometimes these pumps are really trashed and we have to machine several components. In this case, we're going to be making a new shaft, we're going to be making some new bushings, cleaning up this impeller, and cleaning up and sleeving these housings. Let me show you the material we got to work with, and we'll jump right in. For the material, we're going to be using this 304 2 1/8 stainless to remake that shaft. They provided me a cast iron bearing sleeve. We'll be using this guy to sleeve one of these housings. We also have some bronze to sleeve another part of a different housing, and then we have some bearing bronze to make some new bushings for the impeller. Let me go ahead and get started with the shaft. So we'll get that chucked up in the pacemaker and go ahead and get started. We're going to start by removing this impeller from the shaft. That way we can confirm the measurements on the old shaft. Shouldn't be on there with much force. Old shaft is going to drop, but it doesn't matter. We're replacing it. There she is. We'll use this old shaft over at the bench just to confirm the measurements while we're making the new unit. Taking a closer look, you can see we have some damage to the shaft. Over here you can definitely catch your nail. This is undercut by like 60 thousandths, and it's not a full radial groove. As you flip it over here, there's no wear, and then on the back here we have like kind of a half moon worn in. And then what is typical with a lot of these shafts is where the bearings rub, that area can get undercut from the bearing spinning on the journal, and that's usually why these shafts get replaced. Corrosion can be another problem, even though this is stainless, depending on the material that is in the actual pump or the fluid, it can corrode these shafts, but this one seems to be pretty good corrosion wise. So we'll go ahead and get this material chucked up in the pacemaker and get started. So in this case, this shaft is running out, and this shaft cannot fit through the spindle on this lathe. So in the past, without the new lathe, we would have to work with it. We'd beat this around true and center drill this, and a lot of people are irritated by that because it's not the right way to do it, but it does work. But in this case, we do have the new lathe, and instead of doing that, what we're going to do is we're going to take this out of this machine, bring it over to the new lathe, chuck it up near the end with this down the spindle bore. We'll face this and we'll center drill it over there. That way when we bring it back, we can use the center drill to straighten this out, and we can kind of bump this around so it's running true. So we'll get this over to that new line lathe. Now that we got half of this shaft roughed out, let's talk about the critical components when it comes to making a shaft. So first and foremost, concentricity is of utmost importance on these impeller shafts, because these parts do spin in excess of 1,000 RPM depending on the pump, sometimes all the way up to 3,000–4,000 RPM. And if we have a lot of run out, we're gonna just create problems. So obviously turning between two centers will give perfect concentricity. However, there are problems with that, namely when you're running a dog over here on the chuck side. Sometimes if you're doing heavy turning, that dog will slip, and sometimes if you're doing threading and that dog slips, you lose timing on the part. So what I tend to do is do a center on one end, chuck up extra material, and then when I'm done, I part off the shaft. That ensures that every feature is concentric because we didn't remove it from the operation during machining, and that seems to work very well for me. The other thing is that when you're doing shafts like this, there are areas that are more critical and areas that are less critical. As an example, this center section here is where the impeller sits. This is supposed to be a clearance fit with about 1/1000th so that you can slide on the impeller or tap it on with very minimal effort. In our case, we had to press it off, but generally this should be sort of a tap fit. The next surface here is a little bit undercut just to get the impeller on, so the size doesn't really matter, but it's usually like 5 or 10 thousandths under here. This area is a seal journal for a rope seal, so the size needs to be pretty spot on. Can be a little bit off on either direction. I like to shoot for on size, if anything maybe slightly bigger by 1/1000. Try to avoid going undersize on that. And the surface finish on this area is important. Not always possible when doing a large shaft. Sometimes you fight chatter, especially out here in the center, but this shaft has some serious mass to it, so we are able to not worry about chatter yet. But we can get a good surface finish here, so that way the rope seal has a nice wearing surface. And then finally over here on the end, we have the bearing seal and we have the thread. So we're getting ready to cut the thread, but I've made mistakes on shafts like this before, and so the bearing journals are the most critical and they are the tightest tolerance. So generally what I will do is I will get the journal within 3 to 5 thousandths oversize. I will finish the entire shaft out, and then I will come back and polish this down with emery paper so that I have 2 to 6 thou oversize of the nominal bearing size, so that the bearing, when warmed up in an oven, can slide right on, and it has a nice interference fit of about 4 or 5 tenths, which is where it should be roughly, give or take. We definitely don't want this undersized, and it can't be so oversized that it's impossible to get on. For the threads, we're going to be using a top-notch threading holder. I like to blue it up, always take a scratch pass. I will be using direct infeed, no angled compound. Everyone does it their own way. I like the direct way, especially on finer pitch. It's less critical. The blue is just there to make it a little easier to see. I'll zero my infeed. Now this is an 18 TPI, so what I will do is I will go over to my threading chart on the wall. For external, 18 is 34 thousandths. We double that, should be 68. What we'll do is we'll thread up to about 62, and then we'll check it with the nut and make our adjustments to get the nut to fit. So we touched off. I'm gonna take 5 thousandths and switch over here to feeds. We'll take a scratch pass and see how we go. Looks like we're good. All right, here we go. It's always a good idea to chamfer first. If you chamfer at the end, you need to re-chase the thread. Now I do have an undercut, so it may have been fine, but sometimes I do forget to chamfer it until the end, and then I got to retrace it. All right, we're at minus 63, so we'll run this. We'll do a spring pass at minus 63, and then we'll get the nut out, see how we're looking. Looks like we're probably close. Perfect. We're going on, but we're a little tight, which is good. Means we didn't overshoot it. So we're gonna take probably 1 thou passes until we get there. We'll test on each pass. So we're at 63, we're gonna go 64. Remember, I think 68 is the book. Honestly, this fit is not that critical. We just need it to go on. Seems like we're loose on the front because of this undercut here. There we go, it tightens up once we're past that undercut. All right, so I need to take off at least probably 2 thousandths, which would bring us right back to 68. Should be our factory. There's 68 right here. There we go, we can get it on, it's a little tight. Oh, there it is, a burr. So I'm actually gonna Cratex this. All we did was Cratex it and wire brush it. And you can see the undercut makes this go on easy, nice and wiggly there. Once we're past that, it's a nice tight fit, no wiggle. All right, but I can get it on by hand. No play at all there. I'll polish this journal a little bit later once everything's cooled down as the last step, but this side is complete. For the next side of the shaft, what we're gonna do is we're gonna use a parting blade and reference off the end. So this parting blade is 120 thousandths. I'm gonna just bring it out a little farther. The next journal is gonna be the same as this. So I'm gonna zero my depth off of this plane, and we're gonna come down the dimension we need plus the thickness of this blade, which is 120. Actually, what I'm gonna do is I'm just gonna take off the 120 in the beginning. There we go. So the edge of this blade is now flush with that. Now we're gonna come down, I believe it is 12 1/8, somewhere in this region. And then we'll plunge down to not quite to 0, but somewhere around that, and that will be the shoulder for our next section. We're just making room for our cutter. There we go. We switched to a CNMG. I think we're gonna get better chip action. The finish wasn't bad, I like DNMGs, but I feel like the finish is slightly better because the chips are less likely to get clogged behind the insert. At least until I can get some better inserts for stainless in the DNMG. I like machining in this way because as I machine, I can make my adjustments over here in the section that I'm gonna cut. So if I set it and I overcut it, I'm overcutting in an area that I'm already gonna cut down. And I try to never move the cutter. Always let it drag back across when you're taking your measurements. 1.771. So right now the DRO is reading 1.750 and 4/10. We'll check that with the micrometer and we should be within 2/10. Surface finish is good. This is a sealed journal. As long as dimensionally we're good, we should be gold. 1.7507, 7/10 oversized, should be good to go. We're ready to cut the keyways in this shaft. Pretty straightforward stuff. What I like to do is use a 2-flute carbide end mill. The 2-flute is good for slotting, minimizes deflection, and we're gonna step this down in several steps. If you go in and try to do it in 2 passes, you're gonna have a little bit more likelihood of oversizing the keyway, and we are plunging in. If we were coming in from the end, it would be a little bit different, but plunging, especially in stainless, is a little harder on the tool. We center found both sides. We'll cut this 3/8 keyway first, and then we may have to move this in the vise to cut these other 2 keyways. With this shaft done, now we're going to work on this impeller.